I'd like to go through a fully worked out homework problem in chapter 3. The reason I picked this particular problem is because it's pretty complex. In chapter 3, you start learning about phase change substances and other substances such as ideal gases. And you learn, in phase change substances, you learn how to determine the phase of the substance. Is it saturated liquid? Is it saturated vapor? Is it a saturated mixture? Is it superheated vapor? And you get pretty good at that. Then you learn about how to evaluate properties associated with phase change substances. And then you start thinking back about what you learned in chapter 2 regarding the first law of thermodynamics for a closed system. And this particular problem is going to combine all of those aspects into one single relatively complex problem. So let's go ahead and get started. This is problem 355. And so let's look at the problem statement and see where we go from there. 1 pound mass of water is contained in a piston and cylinder assembly, and it undergoes a power cycle, shown in the sketch, in the temperature volume diagram below. Each of the 4 processes, for each of those, there's 4 processes, evaluate the work and the heat transfer, each in units of BTUs, and then a second part says for the overall cycle, evaluate the thermal efficiency. We're only going to spend a little time on thermal efficiency because you're going to learn a lot more about thermal efficiency of a power cycle in chapter 5. But we're really going to focus in this solution on evaluating the work and heat transfer for each of those 4 processes. So let's get started. Let's see. Key words. We start out with, it says piston and cylinder assembly. So in my sketch, do you see that I've added a piston and cylinder? I've taken purely the screenshot of the temperature volume diagram. A reminder about pounds in your textbook. And so notice here, it just says 1 lb of water. Well, when you see in the textbook, when you just see lb, you need to be seeing and thinking 1 pound mass. And so that's a critical point about this textbook is they take a little bit of a shortcut that can be uncomfortable for students. So when you see lb in the textbook, think 1 pound mass, 1 lbm, pound of mass. And let's see how that's different than looking at a pressure. Here's a pressure of 700 psi, pounds force per square inch. And the textbook correctly spells this pressure out, pounds force per square inch. And so it is important and can be confusing for students in recognizing that a pound mass is totally different than a pound force. Pound force is a unit of force. And a pound mass, of course, is a unit of mass. So I got off track a little bit, but that's an important point to make. Another thing is BTU. This is a unit of BTUs. What is a BTU in the first place? Well, a BTU, the unit BTU, is a British thermal unit, okay? And a BTU is associated simply with units of energy. You think, well, is there a little history behind a BTU? What does that mean? I thought I'd just quickly put in how the unit BTU emerged back in the 1800s. And it's defined as, in sort of in general, a little loose definition is 1 BTU is the amount of heat energy, the amount of heat needed to raise 1 pound mass of tap water by 1 degree Fahrenheit. So that's really the informal definition of a BTU. BTU is a unit of energy. And so functionally in your class and as a practicing engineer, here's a units conversion. 1 BTU equals 778 foot-pounds force. And then I've written this out in sort of the way I deal with units conversions, and that is the number 1, unity without units, equals 778 foot-pounds force divided by 1 BTU, or alternatively, unity equals 1 BTU divided by 778 foot-pounds force. So that's what a BTU is all about. So now let's go about solving the problem. We're trying to find the work out and the heat added for each of the four processes. And so as I'm planning my work, I'm thinking, let's see, I'm going to run backwards. At least in this given sketch, you see it's a temperature volume diagram. I can't see anything associated with work when I'm looking at this temperature volume diagram, but by golly, if I draw in my solution a pressure specific volume diagram, I can visualize the work done for a closed system undergoing a quasi-equilibrium process. So this helps me to plan my work and easily plan the work out for each of the four processes. So let's see where we're going. Process 1 to 2. We're starting out as saturated liquid at 700 psi, pounds per square inch, and we're moving at constant pressure and constant temperature to state 2, which is saturated vapor. So there's process 1 to 2. Now, can you visualize the work done for that process 1 to 2? I think the answer is yes. It's the integral of PdV. That's the fundamental. And so, look, I've drawn specific volume in the X. And so actually work equals the integral of PD capital V. That also equals the integral of P times mass times the integral of PD little v. Work is the integral of P dV. Okay, easily I see the work is a positive number, 1 to 2. How about 2 to 3, this constant volume process? What's the work that's done from process 2 to 3? That's 0. dV is 0, no change in volume. That's easy. I'm going to write that down in my solution. The work out from 4 to 1, from 2 to 3 is 0. 3 to 4, I'm going at constant pressure from right to left. Okay, I've got a saturated mixture here at state 3, H2O mixtures, and I'm going to state 4 at constant pressure, 70 psia, pounds force per square inch, also to a saturated mixture, but a much lower quality. Can I visualize the work from 3 to 4? I think so. It's a negative number. It's this rectangle that I'm trying to scope out here on my screen, but it's a negative number, isn't it? I'm integrating right to left, so the work out from 3 to 4 is less than 0, okay? And that's going to be little w, BTUs per pound mass, since I've got little v4 minus little v3. I hope you're staying accurate with that. We'll go through the details, the numerical details in a second. 4 to 1, no work done, constant volume. And so do you see that in my solution, I have shaded this area within the rectangle. This is a special type of process called a cycle. 1, 2, 3, 4, 1. Notice our ending state is exactly equal to the beginning state. That's a cycle. And so the net work done is the sum of all 4 works, and you can satisfy yourself that the shaded area inside the rectangle is the net work for a cycle. You're going to learn a lot more about this in chapter 5. For right now, let's not worry about it too much, but do be satisfied that you can dissect each of these 4 processes and you can visualize the work out for each one of them on a PV diagram. Why? Because it's a closed system and each process undergoing a quasi-equilibrium process. So it is my hope that you see, at least I can get a 50 on this homework problem because I can calculate and record all 4 work values. That's half of what's being asked. Now, and when we go back, so notice here, you're going to need specific volumes, aren't you? You know how are you going to get the specific volume at state 1? How are you going to get the specific volume at state 2? How will you get it at 3? How will you get it at 4? And you're going to need some other properties as well. So that's my commercial. If you don't know how to get properties like specific volume, like internal energy of phase change substances, I want to chase you towards my YouTube channel, How to Evaluate Thermodynamic Properties. And the title of the video is called Property Evaluation Demo. It's a 30-minute set of example problems on how to evaluate these properties of phase change substances, particularly like H2O. Also, now, the next part of the homework problem is determining the heat transfer. And we haven't said anything about getting the heat transfer yet, have we? The only tool that you have in your toolbox so far on determining the heat transfer is the first law of thermodynamics. And this is a closed system, okay? And so I want to suggest that you do look at another one of my videos. If you're not familiar with the first law for a closed system, here it is. I've shown it in red. Qn, heat transfer in, minus the work out. Hopefully you got a pretty good feel for getting that, equals delta U, the change in internal energy, delta capital U. That's going to be the mass, 1 pound mass, and the problem times delta little u. Okay. And you're going to need all 4 internal energy value properties to get the heat added for each of the 4 processes. Okay, so you're going to use the first law to get the heat transfer values after you've gotten all 4 of the work values using integral PDV. First law for heat transfer. I hope you see the roadmap for where you're going. Okay. Some basic ideas. We've got a closed system. It's H2O. It is a phase change substance. It's undergoing a cycle, and you know the mass contained in the piston and cylinder. We drew a PV diagram to visualize the work done for each process. The thermal efficiency, I don't want to spend much time on because you're going to really become an expert in thermal efficiency of a cycle in Chapter 5. In fact, I'm just going to skip over this for right now. You can go back and look and study if you like, but for this video and for good time use, let's just work on determining the work and the heat transfer. Okay, so we've drawn a PV diagram. We're going to get the work values first, and then we're going to use the first law for a closed system as a primary tool to get the heat transfer values. Okay, I think here, let's see, I'm going to move my Zoom business around here a little bit. You're planning your work. Let's study on process 1 to 2. I've got a little thumbnail of our process on our PV diagram, 1 to 2, constant pressure. Okay. So what we're gonna plan ahead a little bit, and we're gonna go to our steam tables because looking ahead towards the work, you know you're gonna need little v2 and little v1. You know you're gonna need those for the work. For the first law, you're gonna need internal energy 2 and internal energy 1, little u2 and little u1. Let's see, and what do you know? Oh, what's the phase of state 1? It's saturated liquid. It's on the dome. How about state 2? That's saturated vapor phase. It's right there on the dome, and you're given the pressure. So you're going to go to your pressure table and you're going to write down 4 numbers, V sub F, V sub G, U sub F, and U sub G at 700 PSI. Okay. You have enough information then to determine the work done from 1 to 2. The work, integral PDV, equals the mass times integral PD little v from 1 to 2. Wow, that's easy. The pressure is constant. You just looked up V2 and V1. If you keep your unit straight, boom, you're going to have the work out. Okay, check. You've got the work out. Now, let's see. How about the first law? Let's write down the first law for process 1 to 2. Qn from 1 to 2 minus W out, just found it, equals delta capital U. That's going to be the mass times little u2 minus little u1. And we planned ahead good enough in our steam table work to write down U sub 2 and U sub 1. Check. You've got Q in from 1 to 2. Got it? Okay, so there's your plan. The devil's in the details, and there's plenty of numerical work to do. Process 2 to 3, constant volume cooling. 2 to 3, here's my little thumbnail. 2 to 3, constant volume. Do you see that by inspection, you can X out the workout from 2 to 3, integral PDV is 0. Okay, so you can jump, that's 0, that's a good answer. First law for 2 to 3, process 2 to 3, Q in from 2 to 3 minus workout, 0, equals delta capital U equals M times U3 minus U2. I just looked up U2, I'm good, but I need U3. How will I get U3? I need to figure out U3. Well, I have to study on what I have. The PV diagram is golden for this. I see that V3 equals V2. I can write that down. Okay. I also know that the pressure at state 3 is 70 psi. I know the pressure. And I know that the phase of state 3 is under the dome. It's a saturated mixture. So there's going to be a value for X3, isn't there? X3, the quality at state 3. And so if you think enough about this, do you see that you can solve for X3? How would you do that? Well, here I've written down, use the definition of quality to find X3. You know V3, you have a number for that. What's V2? Well, that equals X3 times VG3. That's a number that you can write down from your pressure table. VG, saturated vapor specific volume, plus what's left over, 1 minus X3 times VF3. That's a lookup at 70 psi. You've got one equation, one unknown. Solve for X3, the quality at state 3. Wow, okay. Well, but I need U. I need the internal energy at state 3. Little u. Wow, I just got X3. Do you see that now I can determine U3 by saying, okay, that's X3, just found it. I can look up UG3 in my pressure table, 70 psi, plus 1 minus X3 times UF3. Look that up in the pressure table. Boom, and I've got U3. I can back up a little bit and immediately solve for the heat added from 2 to 3. So that's our planning. So now we're halfway there. Okay. We're going to 3 to 4, I believe. Yes. 3 to 4. Here's my thumbnail. 3 to 4. Okay. Let's see. Constant pressure process. Constant pressure, 70 psi. I'm integrating from right to left. I can visualize the work term. It's the area under this curve, the 3 to 4 rectangle, but it's going to be a negative number. Okay. And so sure, wow. And so let's see, V3 I just found. Okay. Wow. I don't have V4. I need to get that. Okay. But once you get V4, do you see that it's simple to calculate the work from 3 to 4? It's mass times P4, known, V4 minus V3. I need V4. How will I get V4? Wow, how will I get V4? Let's see. Oh, I see. I don't even have to do any math, do I? I see that V4 exactly equals V1. Looking at my PV diagram. Shame on me for not seeing that immediately. Thank goodness my PV diagram was there. Okay, so we're good. We're good on the work from 3 to 4. M times P4, V4, which is the same numerically as V1, minus V3, which you already had from previous work. That's also V2, isn't it? Okay. Now the heat transfer. All right, we just got the workout. Qn minus the workout, just got it, equals delta capital U equals the mass times U4 minus U3. I've already got U3. I need U4. Wow, how will I do that? Wow, okay. Well, there's some quality associated with state 4. It's under the dome. I need to find X4. How will I get X4? Well, it's going to be the same approach as process 2 to 3. I see that V4, which is known, equals X4, unknown. VG4, that's a lookup at 70 psi, plus 1 minus X4 times VF4, lookup at 70 psi. One equation, one unknown, solve for X4. Solve for X4, okay. Now that I've got X4, I can immediately calculate U4 using the definition of quality. U4, unknown. X4, just found it. UG4, look up at 70 psi, saturated vapor internal energy, times 1 minus X4, UF4, saturated liquid at 70 psi. Okay, so a lot of details. The nice thing about a video is you can rewind if you need to, slow it down, speed it up, whatever you want. So don't get me wrong, this is not simple. It's kind of complex, but hang in there, go through the math, spend the time to get this problem, because you're going to have something just like this on quizzes and tests. You must master this process. And also, do you see, it's not formulas. So nobody is working you through, do this formula, do this formula, do this formula. You've got to figure this out on your own, in your head, and with the help of a pressure volume diagram that you drew. All right, enough preaching. Solve for the first law for Qn from 3 to 4, and you've got process 3 to 4. Finally, process 4 to 1 to complete the job. No work is done. 4 to 1. Integral PDV is 0. Okay. The nice thing here on process 4 to 1 is you've got all the properties you need. You just found U4. You've already looked up U1. And so the heat added is simply the mass times U1 minus U4. You're going from 4 to 1. That's why it's U1 minus U4. Okay. And it looks like I've got a copy and paste error. This needs to be, instead of solve for the first law for Qn from 4 to 1, not 2 to 3. That was my copy and paste carelessness. Okay, the thermal efficiency, I'm going to breeze over this slide. The thermal efficiency that you will learn more about in chapter 5 is defined as the energy sought over the energy that costs, which is standard definition. Don't worry about that. It's Greek letter eta is the subscript for thermal efficiency. It's the net work. It's that area. Let me go back up. It's the area, the shaded area within the cycle. That's the net work divided by the heat that's added. And that's only for processes that add heat, not processes that take heat out. Okay. But that's the way to get thermal efficiency. We're not going to spend much time on that. Now we're going to go to the detailed numerics of solving this problem. Here's the way I would solve it. Now, remember, I have solved a lot of problems, so I kind of have a skill of planning ahead a little bit, planning my work. I know what I'm going to need. So the first thing I'm going to do in my solution is I'm going to go to my pressure table at 700 pounds per square inch, pressure table, and I'm going to write down 4 numbers, VF and VG, cubic feet per pound. I'm going to write down UF and UG. That's going to be for my first law. I'm just going to write those down on my solution. The next thing I'm going to do is go to my pressure table to 70 psi, because I'm going to have that same problem down in those states as well. So of course, you see state 1, phase of state 1 is saturated vapor, a saturated liquid, VF, UF, saturated vapor, VG, and UG. Okay. I'm going to need to write those same numbers down at 70 pounds, 70 PSI, because I've got to solve for the quality at states 3 and 4. All right, so I do the same drill here. I'm going to go to my pressure table and write down VF, VG, and also UF and UG. So that's the pre-work that I've done. Go into the back of the book, writing down those properties. That's some work. That takes some time. Okay. Now I'm going to determine, and let's remember how we planned our work. We start process 1 to 2, and we start with the work out, integral PDV. I'm going to write down, given the mass of the closed system, 1 pound mass. Okay. V2 and V1, I wrote down from above. Integral PDV at 700 PSI. I wrote down, I entered 700 pounds per square inch, but I'm going to immediately transform that to pounds force per square foot because I can plan ahead and I know I need to be working in pounds force per square foot to get my units straight. And so 700 times 144, 144 square inches in a square foot. That's how I know to multiply 700 by 144. So I've got lots of square inches in 1 square foot. So I've got a huge pressure, looking pressure, because it's pounds per square foot, not over per square inch. So there's my pressure. So my work out, and keeping my units, integral PDV. So it's M times pressure times the change in specific volume, cubic feet per pound mass. There's my M. That's going to cancel my per pound mass. And so do you see, hopefully you can do this in your head, that the units of pounds mass times pounds force per square foot times cubic feet per pound are going to have units of pounds force feet, foot pounds force. Foot-pounds force, some huge number of workout 1 to 2. I've got to write down my conversion. 778 foot-pounds force equals 1 BTU. And so I will apply my unit. So I've got to, let's see, I've got workout and foot-pounds force. So I've got to divide by 778 to get BTUs. I think I can see that visually here. Or if you're doing pencil and paper, you show that in your pencil and paper solution to get the workout from 1 to 2 is 82.34 BTUs, British thermal units. Makes sense. It's a positive number. Let's say recap. I immediately change pounds per square inch to pounds per square foot. V has got units of cubic feet per pound. And so I ended up with a work value numerically in foot-pounds force. I had to convert that to BTUs. Okay, great. So, and my workout is greater than 0. Okay, let's see. What's next? The workout for process 3 to 4. So 2 to 3, the workout, I would write down on my solution. The workout from 2 to 3 is 0. Okay. 3 to 4. 3 to 4. The workout is going to be a negative number. I think you probably see the drill. Okay. Let's see. Our pressure is 70 pounds per square inch. Transform that into pounds per square foot, multiply by 144. Notice I'm writing my units out. I'm not just writing numbers down. Okay. The work out from 3 to 4. M, 1 pound mass. P, 10,080 foot-pounds force per square foot, or pounds force per square foot. Delta V, negative 6406 foot-pounds force. Conversion, 778 foot-pounds force for BTU gives me negative 8.23 BTUs. And I'll just log that. Okay. Woo, I've got all 4 of my work values. I've got half credit now on my homework problem. The next thing in our planning was to determine the quality at states 3 and 4. Okay, here's how we do that. Okay, so state 3, it's under the dome. Okay, it's a saturated mixture. So let's see. I've got, so for state 3, okay. I've written down at 70 psi my VF and VG values. There they are. Okay. I've written down V3, 0.656. Okay. So how do I get X3? How do I get X3? Well, I've got a visual. It's a ratio. It's V3 minus VF. Okay. It's this number minus VF, all the way over there, divided by VG. It's off my screen. It's over there at saturated vapor. There's VG minus VF at the dome. Okay. So my X3 is 0.103 and change. It's a low quality. X is 0.1. X3 is 0.1 quality. Same idea for finding state 4, the same mathematics. I'm using the same VF and VG. I'm using a different V value. I see that V4 exactly equals V1. There it is, 0.02051 cubic feet per pound. So numerically, X4 is 0.0005, nearly on the dome. That kind of makes sense because look at the way graphically it turned out on my PV diagram. Very close to the dome, but not on it. It's still a saturated mixture, mostly water. Okay, so we have just found X3 and X4 using the specific volume values at 70 psi. Okay. You may want to go back and replay this to see how I did it, but the way you get to the X values is by studying your PV diagram. Let's see, we saw that V3 exactly equaled V2. We saw that V4 exactly numerically equals V1. So we use that along with VF and VG in our pressure table, 70 psi, to solve for X. Okay, great. So that is a slide that might take you a while to numerically get these. Okay, that's hard work. The next thing in our planning phase is we need internal energy for 3 and 4. Well, we just found X. Okay, and I see on this slide that I didn't repeat what X was. Okay. So I just wrote down U1 and U2. U3 is going to be UF plus X3 times UG minus UF. And I just have to apologize that I didn't write down from above what X3 was. Seemed like it was about 0.01. Okay. U4, same type of idea. We just found X4 from the previous slide. And so we're going to just plug and chug to get values of U3 and U4. Now, thinking ahead to the first law, remember, I've got a delta capital U. Here's what I did in my solution. I just multiplied my little u values by M, which is 1 pound mass. So numerically, they're matching, but I want to be sure to be very clear that I'm calculating capital U's in my solution. Okay, so I guess I'll have to apologize that in this slide, I did not write down the numerical value for X3 and X4. I'll go back a slide to see that we just found those values using specific volume. Okay, so we've got internal energy values in our planning phase. That's what enables us to go to the first law, solve for Q, since we've already found all the W's. Okay, I wrote down all my work out values. Okay, and so now I can summarize the cycle. I can apply my first law. I think I didn't show my work for each 4 of my processes, did I? Let's go back and check to see if I did do that. Well, no, I did not. So I guess I'm going to have to apologize for not showing a complete good solution of applying the first law to solve for the heat added. Well, let's see, maybe I can do this in words in my cycle summary. Do you see here? Remember that Q, in the first law, Q in minus W out equals delta capital U. That makes sense? Okay. So can we visually see if we're solving for Q in, we can write down delta U plus W out. In other words, I can move this over to the other side. Okay. And so I'll do the math to solve for these Q in values. Okay, so that's a real gap in the solution I'm showing here. I didn't show the work for the first law for all four processes. So shame on me. Thank goodness I summarized my work here. Okay. And then finally, the thermal efficiency is the energy sought over the energy that costs. We're just going to gloss over that because to get the heat added, I added up only the positive values for Q. So I added up 710 and 216 to get this heat added 926 and calculate the thermal efficiency, which is a low value of 8%. It's terrible thermal efficiency, and you're going to learn a lot more about that in chapter 5. So let's not worry about thermal efficiency much, and we'll move ahead. Okay. So to criticize my own work, near the end of the solution, I did not show my 4 first law applications numerically to solve for Q. But hopefully, if you can go all the way back to the planning phase of the solution, you'll see the fundamental of the first law written down there. And so I'm sorry I didn't show that numerically. I hope I explained that good enough. So what's the recap of this worked out complex solution? Start with a sketch. I had to draw a pressure volume diagram because it was not given. Only a temperature volume diagram was given, and you cannot visualize work on a TV diagram. You can only visualize work on a PV diagram for a closed system undergoing quasi-equilibrium process. We planned our work. We spent some time planning before doing. We started with the fundamentals. For this problem, it was the integral PDV for work and the first law for a closed system. Blindly using formulas is an absolute loser, and I hope that the solution to this has shown you that trying to fish out formulas in a textbook is a losing proposition for a complex problem like this one. You'll never find a set of formulas in the book that guides you to the promised land. Another thing on this English system problem was we had to carefully check our units. We were dealing in BTUs, British thermal units, foot-pounds force. We had to transform pressures from pounds per square inch to pounds per square foot. So checking units as you went along was critical. And also, when you get to the final result, expressing your units complete with expressing your numerical results with units is an absolute must. So that is my worked out solution. I'll have to apologize that I didn't show enough numerical work at the end on the first law, but I think you can probably figure it out. So good luck. I hope this helps you with the complex problems that are growing. It only gets more and more complex once you get through chapter 3, but this would have been a problem that will take you a significant amount of time in chapter 3. So stay tuned for my next solution where I'm going to try to illustrate a problem in chapter 4.